Okay, okay.
Let's do it, Simon. Uh-huh.
Okay, perfect. Then I will continue then.
Please.
So let me just start by explaining what this dynamic average consensus problem means. So we start with a more known setting, which is, let's say, static average consensus or just standard consensus, which is in a case in which you have these n agents represented by these little points. So these can be robots or computing units or whatever you want. And these are connected through a communication graph, right? So each of these lines represent a communication link between two nodes in the graph, two agents, okay? And at each node, usually we have some, let's say, measurement or some quantity of interest. We call it Si for the agent I. And the goal for the consensus problem is, for the average consensus problem, is to estimate this static average, okay? So you have these constants distributed across a network, and you want to compute this average. And note that this is a global quantity, right? So if you had access to all the S at the nodes, you can compute this average, of course, but the challenge is to compute it in a distributed fashion. This is at each agent using just only local interactions, right? So for dynamic average consensus, we put another degree of difficulty. And instead of having static values at each node, we have dynamic signals, right? So this is like a continuous stream of measurements, right? Represented by these time varying signals. And we have one for each of the nodes, okay? And now in this problem, what we want to compute is now the time varying estimate or the time varying average of these signals, right? So that's why we call it a dynamic average consensus, okay? So this is the problem. And of course, typical static average consensus solutions may not work for this problem due to the dynamic part, okay? And up to this point, this is what in the literature they call dynamic average consensus. So this problem has been studied for more on the robotics and distributed optimization side. But of course, we can extend this a little, and we may also want to estimate derivatives of this average signal, right? So in this case, not only estimating the average of these time varying signals, but also the derivatives. So this is what we call the distributed differentiation problem. And it's related to the differentiation problem in the sense that you may want to differentiate a signal, but this signal is, let's say, constructed from pieces that are distributed across a network, okay? So you cannot compute this derivative using a standard differentiator, okay? So this problem has very nice applications, particularly in distributed state estimation, for example, but it has also been used for many other more complicated problems, very high dimensional, such as dynamic map merging, for example, in my laboratory. This is what they call distributed SLAM. And it's dynamic because you can have a map in which you have many dynamical objects, and you can estimate the state of the map using these time varying capabilities, right? But more recently, it has gained a lot of attraction because it can be applied directly for distributed gradient flows, essentially for optimization. So for distributed optimization, and you know that has many applications in nowadays machine learning. Well, one of the key components for popular algorithms is dynamic average consensus. Okay, so I just want to say that it is an interesting problem. It has many interesting applications. So we may want to try to solve it using what we know from our community. Okay. So first I want to point out some parallels with what we know about differentiation. So in differentiation, which is a related problem, but in this case is just trying to differentiate a signal, which is equivalent to observe this unknown input system, right? So you have a chain of integrators, and in the last state, you have an unknown input, which is given by the n+1 derivative of some signal, S, okay? And usually we assume that this signal is bounded by some constant L, right? And developing an observer for this system is developing a differentiator, right? Roughly speaking. So I just want to show some historical developments of how these solutions for this problem have arisen through history. And I want to compare it with how the development of dynamic average consensus have been. So first, of course, you may try to build, let's say, a linear observer for this system. And of course, that won't be exact. That cannot be called a differentiator by itself. But you can have the solution, which is a high gain observer. You can have this very special case in which this is not properly a differentiator, because in the m equals 0, which is just a single integrator, you don't differentiate anything. But you can have the intuition that using standard sliding modes, you can stabilize the system by rejecting these disturbance, right? If we go further in time, we have the super twisting algorithm, which allows to construct first order differentiators, right? And then afterwards, we have the arbitrary order differentiators, right? This is very important because when these algorithms appeared, the original proof is based on a high gain argument, right? And homogeneity to prove finite time convergence. And what's interesting to me is that in this proof, you can show that there exists some gains, sufficiently big gains, that makes this algorithm work. But up to this point, you have to find them by simulation, okay? Until the point in which you have Lyapunov functions, which introduce more systematic rules for the gains, right? So this is the let's say the milestone for differentiation. Now let me show the milestone that we have for dynamic average consensus. So for the problem that I explained before, it started with linear high gain schemes, right? So if you find the literature from when this problem started to be studied, you will find linear algorithms with high gain arguments, right? So it's very similar to a high gain observer. Then, until very recently, 4 years ago, George and Fridman introduced sliding modes to the game, and this allow us to, let's say, naturally extend or try to extend this well for high order sliding modes. So it's trying to answer the question: what is the distributed form of a super twisting, for example, right? So this is what we call distributed differentiators. Okay. And interestingly is that we are following, let's say, or taking some lessons from high order, from developments of the differentiators in order to construct these differentiators, in the sense that the proof that we have at the moment are based on a high gain arguments and homogeneity. Okay, this makes this makes the question if some future work can be used to extend to Lyapunov functions. Okay, so I will return to this slide in a moment. Let me just say that the observation key is that history is repeating again, right? So the problem is similar, and we may try to take some lessons from what we know in high order sliding modes for the development of differentiators to this problem, okay? So in order to explain you what our solutions are for this problem, I will explain, let's say, basic case, which is static average consensus, and I will explain the design philosophy for algorithms in this topic, right? So I will explain for static average consensus, and then I will explain it for a dynamic average consensus with okay. So first of all, usually you have for each agent some internal state, internal memory, which we call xi, and we initialize it. I don't know if someone has his microphone unmuted. Okay. Yeah, I will continue. So each agent has an internal memory xi, right? And you initialize this memory to the values that you want to compute the consensus, okay, the average, okay? So each agent has a capability of sharing this internal memory with its neighbors, okay? And this is the most popular, let's say, update rule that you have in order to have a average consensus, which is essentially update the internal states according to these terms, which are the disagreements between agent I and agent J, which is its neighbor, right? And this is a very well-known result, and is that if the graph is connected, well, as you advance in time, well, each state approaches the average that you wanted to compute, given this initialization, which is very important, okay? And the analysis is very simple. So this is an analysis that we will keep using again and again. And first, we want to write this in a vector way. So essentially, we write a vector with the states of the agents stacked, right? And when you write this linear system in a vector fashion, you arrive that the system matrix is the Laplacian matrix. The Laplacian matrix is a very special matrix for graphs, right? And it has this structure, right? So you have one matrix that has a diagonal with the number of neighbors for each agent. And you have here the adjacency matrix, which has this information about which agent is connected to which agent, okay? So what does consensus mean? So consensus mean that the vector x has all components the same. Okay, this is x is just one scalar, let's call it alpha, times the vector of ones, represented by this symbol. So the analysis is, or the main technique for this kind of problems is to decompose the vector x into components. First, one is the projection of x towards consensus, which is what we want. And the other is a component orthogonal to that, right? So essentially, we want to get rid of this component such that we arrive to consensus, okay? We want to analyze the dynamics by separates. Interestingly, you design the algorithms to have decoupled dynamics, right? So we want the dynamics for this term and this term to be decoupled, okay? For the agreement is the component that is parallel to consensus. You can show very easily that its dynamics are null, right? So this value will be kept constant. And this is important because if it is kept constant and at the initial time you initialize the values with this with the quantities of interest, well, this quantity will remain constant at the average that you want to compute through the whole time, right? Now for the disagreement dynamics, you can show very easily as well that the dynamics has very similar structure. And if the graph is connected, you can show that this converges to zero, right? The proof idea, which will be very important later, is that you can use a very simple Lyapunov function to arrive at this differential inequality, right? Which will allow you to have some sort of robustness, okay? So this is linear, right? So the main design principles or the design philosophy for this kind of problems is that you design, let's say, the dynamics of your memory using local interactions, such that first you can make this decomposition in something parallel to consensus and the disagreement, right? Such that the dynamics are decoupled. I mean, the dynamics of this does not depend on the dynamics of this. That the agreement converges to something of interest. In this case, it was that it converges to the average of the quantities of interest, and that the disagreement converges to the origin, okay? So this is the main, let's say, philosophy that we will keep undergoing, okay? Now, for dynamic average consensus, which is a more interesting problem. So this is the most typical algorithm that you use for dynamic average consensus. We're still in the linear regime, okay? And as you can see, it's essentially the same system as before, but we introduce here the derivative of the signal that you want to, for which you want to compute the averages, okay? Of course, if these signals are kept constant, right, this term just disappears and you recover the original algorithm, okay? And you may say, okay, how do I implement this? I require this derivative. You may say that you can introduce a differentiator, but a very simple trick allows you to implement an equivalent system, right? Which does not require you to inject these derivatives, okay? So this is what you implement in practice, right? It does not require to differentiate any signal, but the system of interest is the one on the top, okay? So we do the same, okay? In this case, we put a vector with the states of all agents again, but we put a new vector which all the signals for which you want to compute the average, okay? And the dynamics in vector form are very similar as before. This is the same term we have for traditional average consensus, but we have this term as well, which is the derivative of the signals for which you want to compute the average, okay? So this, in some sense, this will play the role of a disturbance, okay? So we perform the same decomposition analysis, right? So we decompose, again, in something parallel to consensus and the disagreement. And when you compute the dynamics of this term, you observe that the derivative of the agreement is exactly the derivative of the average signal, okay? Which means that for appropriate initialization, right, it is exactly the average signal, right? So the agreement is exactly the average signal, which means that in some sense, you already have the problem solved, right? So in some sense, you have the solution already in the state. You just have to get rid of the disagreement, right? So the solution is already there for the whole time. You just have to get rid of this, let's say, fog, okay? The disagreement dynamics, on the other hand, have these dynamics, which from which you can see where the problem starts to appear, okay? Essentially, these are disturbances of the form. The components of this vector are the derivative of the signal minus the derivative of the average, right? So if you're not in consensus, this is a disturbance. And usually in the literature, you assume that these are bounded by some constant L, okay? And you have this other term, which is linear and has some form of robustness, of course. For a sufficiently high gain, you can achieve some form of convergence to a neighborhood of the origin, but it is not exact, okay? And we know this because we can use the same Lyapunov function as before, okay? So the main result that the people in this area use is that if the graph is connected, well, you have bounded error, okay? Bounded disagreement in permanent regime, okay? Which means that each xi only approximates the average signal, okay? So first observation is that if the disturbance is zero, let's say if we are trying to compute average of signals that are constant, you can make this be equal to zero, which is reasonable since this is a static consensus. This is equivalent to static consensus, okay? But otherwise, exact convergence will not be obtained, right? You will always have a bounded steady state error if the signals are persistently varying, okay? And the second observation is that if you increase kappa, of course, you can make this smaller, okay? But you will be more sensitive to noise, okay? Which is expected as well. So that's the most that you can achieve with a linear algorithm. And most of the current solutions that you find in the literature are based on these two arguments. So you have a linear correction term, and you have a high gain argument to achieve, let's say, approximate consensus. Okay. So you can find this all this in a very useful tutorial here. Now, the role of this disturbance motivates you to try to use, let's say, sliding modes, right? So you have a disturbance, you may want to reject it using this continuous term. So this is what you can do. For example, this is the same algorithm as before, but here we introduce our favorite discontinuous functions, right? So we have the sign of the disagreement terms instead of just the disagreement terms, okay? So this is what George and Fridman introduced 4 years ago. And if you write it in a vector form, this is a little bit more complicated, right? But essentially, you can write it as follows. You have this matrix D, which is essentially the incidence matrix of the graph. An important part of this product is that this product contains all these differences, okay? So essentially, you compute the sign of the differences, which is what we have here, and we write the rest using the transpose of this incidence matrix, okay? So yeah, this is the vector form of the dynamics for the discontinuous protocol. And we make the same reasoning again, okay? We will decompose the vector x into components, one parallel to consensus, one orthogonal to consensus, and see what happens. For agreement, we have something similar as before. For a particular initial condition, you can achieve or you can conclude that the agreement is always exactly the average signal, okay? And for the disagreement, you have something similar as before, where you have this disturbance, which we could not reject using the linear protocol, but now we can, okay? We can pick this kappa sufficiently big, and you can compute exactly how much it has to be in order to have a complete disturbance rejection, okay? So if the graph is connected, you can show that the disagreement goes to zero, okay? Exactly in finite time. And this means that xi is exactly the average signal after some finite time. So this is an improvement with respect to average linear algorithm for dynamic average consensus, okay? The advantage is that it is exact, right? So it converges exactly. It converges in finite time, so it has some more robustness properties, and it has fast convergence. The disadvantage is, of course, that you have chattering, and actually you can show that the chattering gets worse as the network increases in size. And the reason is that for one message to arrive from one node to another, right, the maximum delay increases with the network size. So so the chattering might get worse in that case. And the other disadvantage is that, well, it computes only the average of the dynamic average, right? It cannot yet compute derivatives. Okay. And these last two problems that we cannot yet compute derivatives and that and chattering motivates the introducing, let's say, high order algorithm for this problem. Okay, and it's what we did. Okay, so the first question that you might ask, what is the analog to a super twisting in this context, right? So recall that this was the original algorithm with standard sliding modes. Okay, so naturally you can come up with, let's say, a super twisting algorithm. Okay, without showing anything still. So you might think that first you have a chain of integrators, right? So for each agent I, you have two states, the 0 and 1. You have a chain of integrators, in this case, just a double integrator. And you have these correction terms with the power 1/2 and 0. Okay. So this has the same structure as the super twisting, but it is adapted to this problem. So recall that in this case, we add all these terms for each neighbor, for each agent. Okay. So in a moment I will show this, but the result is that if you try this algorithm, well, it works fine. And actually you can show that if this term, which is, let's say, the differences between the second derivatives of the signals and the second derivative of the average signal is bounded, right? So the first state for each agent can converge to the time varying average, and the second state will converge to the derivative of such average signal in finite time. Okay. So this is already achieving, let's say, distributed differentiation. Okay. And of course, the arbitrary order extension of this is similar. You have a chain of integrators here, and you introduce here these powers, which you choose them in order for this system to be homogeneous. Okay. So it is very similar as a differentiator, just adapted in some sense to this problem. Okay. So this is the system that we implement using these, let's say, auxiliary variables. But the variable that you want to study is x. So if we analyze the system in x, we have a similar structure, just that we have in the last state the n+1 derivative of the local signal. Okay. And if we write that in a vector form, okay, in this case, we have a vector for each mu state. So recall that each agent has here up to m states. So for each mu, we have this vector, where each component is one agent, okay? So we have this structure in vector form, and it keeps looking more and more as a differentiator, right? So now we will apply the same decomposition analysis to this system. So each of these vectors, we will decompose it as something parallel to consensus and some disagreements. Okay. So the agreement part, you can show that it has this dynamics, which is a chain of integrators. And from here, you conclude that for appropriate initial conditions, okay, each of these variables will or are exactly equal to a derivative of the average signal. Okay. So this is for the agreement. For the disagreement, you have this other system. And essentially, this now is what plays the role of a disturbance. And you will try to reject it using this discontinuous term. Okay, that's the intuition, right? But that is not so easy to show, right? So we have this system, and we want to show that the disagreement goes to 0. So how can we show it? Well, since it has the similar structure as a differentiator, we may start using a similar proof idea as in the proof for the differentiator. So we will try first to write it in a recursive form. We will show contraction for each variable one by one in a recursive way using induction. And afterwards, we will use homogeneity to show convergence in finite time. So that's the first proof idea that you can come up, even before trying to come up with a Lyapunov function. Okay. And just to convince you that this works, I just will show one very interesting connection between these systems. And is that for tree graphs, the connection with a differentiator is very evident. Okay. So if you have a tree graph, the incidence matrix is of full rank. Okay. So that you can make this transformation, this change of variables. And if you make this change of variables and you rearrange the equations appropriately, okay, you will obtain this form. And essentially, all equations except for the first one have exactly the same structure as the differentiator in recursive form, okay, for appropriate disturbance, of course. So that, and also that if you go to the original differentiator paper, the role of the noise is played by this first state. So you want only to show that this first state also satisfies some sort of contraction, okay? And you can do it very easily since it's a first order system, okay? So the result that we have for arbitrary order differentiator is that if the graph is connected and these terms are bounded, okay, we have that in finite time, each of these states converge to some derivative of the average signal, okay? And by using just the homogeneity properties of the system, if you have noise bounded by some bar epsilon, you know that the accuracy has this typical bound, which is, let's say, inherited from the structure. And when you have, let's say, discrete updates in these parts, well, you can show that, let's say, the chattering can be characterized by this term. So these are features very similar to a differentiator. Okay? Now, this works for appropriate gains, right? So up to this point, you know that this works for sufficiently big gains, okay? So just as an example, I will show you just briefly how this works in practice, right? So for example, consider a circular graph of 10 nodes. Consider that the signals you want to compute the average of are just sinusoidals. And to simulate, for the moment, use explicit Euler discretization, okay? So this is a very typical behavior. So you have some transient for the states. We are plotting the first state, not the zero state, so that this will converge to a derivative of the average signal. And this will converge to the average signal in a finite time, okay? So they reach consensus to this signal. So essentially you're achieving what we wanted before is an exact computation of the distributed derivative, okay? Just an example of how it looks when you compare different types of algorithms. So for the linear algorithm, which is the first that I presented, you have this type of behavior for persistently varying signals, which is that you reach something close to the average, right? But you have this bounded error. For a standard sliding mode or a first order sliding mode, if you want to call it like that, when you discretize by, you have this chattering effect, right? And this chattering effect can be dampened in some sense by means of using high order algorithms as the ones that I presented, okay? So some extensions of these algorithms and some open problems are the following. So I presented just the basic, let's say, algorithm, right? But there are many other extensions that you may want to consider. So recall that for this algorithm to work, we needed very particular initialization values, right? So those initialization values may break when some agent disconnects from the network or when you merge two networks, okay? So these kind of situations is what they call open networks. And in order to get rid of those initialization issues, well, you can use additional machinery. This is something that we published some years ago. You can also extend this to have multi-leader in a multi-leader setting, right? And also to have prescribed convergence. Also following very similar arguments as we know in high order or in differentiator development, you can achieve some proper discretization for this kind of algorithms. And you can achieve also weighted consensus as well, okay? So let me return to these slides, which is a comparison of the development of differentiation with the development of algorithm for dynamic average consensus. And up to now, what we have at this point is that, of course, for tree graphs, the gains can be obtained from robust exact differentiators due to this similarity. There is a direct connection between robust exact differentiators and the distributed differentiator for a tree graph. For general graph, we have only showed that there exist sufficiently big gains, sure, and this can be obtained, let's say, for a family of graphs through simulation, okay? So the next step might be to try to find some Lyapunov function which may help us to formalize this gain design, okay? So this is what we, let's say, see from what we have learned in the differentiator development. And of course, in this case, for the distributed case, some conservativeness. We know that some conservativeness will be introduced using Lyapunov functions, particularly when we increase the network size. Okay. So just to draw some conclusions, which are important. So the main thing is that I wanted to point out some similarities between the historical development of these two things, differentiators and dynamic average consensus, and that the distributed differentiation design is based, let's say, or is inspired by homogeneity and differentiators. Okay. And we show that these lessons that we learned in the development of exact differentiation are useful also for the distributed case, but that there are still also some fundamental open problems. The main problem that I see right now is gain design. Okay. And I believe that both the multi-agent system community and the high-order learning mode community can be benefited from results in this area, right? So up to now, there is not so much overlap, but I believe that by working in this particular intersection can be beneficial for both communities, okay? And that's essentially what I wanted to present today. I am ready to have some interesting discussion.
Thank you, Rodrigo. I'm not sure that the discussion will be interesting, but at least I'm really I'm really pleased to tell you that you found another field to develop our algorithms. And so I would like to ask you if prescribed or predefined or fixed time convergence is working here and could be it helpful or not.
Yes, I mean, I believe it might be very helpful, right? So essentially, for many algorithms which use dynamic average consensus blocks, let's say, usually you want to study if they converge as the other algorithm converges, right? So having fixed time convergence for the dynamic average consensus might be very helpful in order to have separation of different blocks, right? Because you usually use these dynamic average consensus solutions together with other things, right? So with a controller, for example, right? So using fixed time notions in this case can be very, very useful, I believe. But this is still a very early or very young era, let's say.
So you mean that you can make cascade converging them one by one or what?
Yeah, but I mean, for example, if you want to have, I mean, for example, in this system, as you can see, it has a very similar structure as a differentiator, and we have fixed time differentiators, right? So maybe we can also borrow some lessons from what we have from what the community have done in that case, and try to come up with an equivalent system for this case, right? So that's one thing that you may do. That's one thing that I see that we can do.
Okay. You know, the other question is connected with our papers, which we are trying to optimize somehow the differentiator gains. I don't know if you ever read or seen the paper we published recently for the second order differentiator and story like that. The point
Yes.
is that so, and the next story, it is reasonable to grow up the precision, to grow up also the order of differentiator, making it more than m as in your case, and then to have better estimation of the signal. Is it
Okay.
reasonable for your case or not?
Up to now, the thing with the gains is still uncertain, right? So I believe that some things will be inherited from the differentiator theory, let's say, but I cannot be sure at the moment. I infer that yes, there will be some connections as you mentioned, but I don't know if they are as clear as. I mean, there will be some challenges in that case.
Okay. Thank you.
For tree graphs in particular, the gains are the same for the differentiator, right? So whatever you learn from a differentiator can be inherited to this kind of problems for tree graphs at least.
Mhm. Okay, thank you. So, please, other comments? I'm not sure that Elio is here because normally. Jorge, maybe you're working also on consensus.
Yes, thank you, Doctor. It's a very interesting topic. I think it is. They have a very promising different fields for applying the idea. What is interesting is that, for example, one topic that we are working here in IPN is the distributed estimation. That could be the idea of a merge the distributed field with the high order sliding modes, for example.
Sure.
The idea is to estimate the states of a common system that is measured by different sensors that are distributed in a network. And yes, please, sorry.
No. It's very interesting because, for example, if you set these signals to some, let's say, common signal plus some noise, right?
Yeah.
So averaging will reduce the noise, right? If all sensors have, let's say, a similar noise magnitude, right?
That could be interesting because you are doing sensor fusion.
Sure, exactly.
Yeah. It's great. I think your work is very interesting, as always, Rodrigo.
Thank you.
Thank you.
Thank you so much.
Okay, other comments? Okay, Professor Levant, as usual.
As usual. Okay. Thank you. First of all, thank you very much for this presentation. It's completely new field for me. It's not very much non-trivial.
Sure.
And I have a few questions. First question is very fundamental, I suppose. So there is a net of these agents, and they are connected with some neighboring agents. There is graph of connection. Graph is itself is connected.
Yes.
So what I lack are some restrictions. Some restriction which doesn't allow us for all, if the graph is connected, why all of the agents cannot just get all the information through the connected graph.
Yeah, so it's a connected graph.
There are no problems.
Yeah, it's a connected graph, but it's not a fully connected graph, right? So, for example, this I don't know if you're seeing the screen, but this agent has only access to its own signal and this neighboring.
Yeah, but it is connected graph, which means that from each node you can go to each node.
Yes, for sure.
In particular, all nodes can have all information. There should be some restriction on it.
Yes, the restriction is that in practice you want to have only have one hop communication, right? So what you're describing is maybe you can send your signal to this node, and this node can send it to the rest of them, and this is what they call flooding. So flooding is send everything to everyone, right?
Yes.
So that will congest the network, right? It will introduce delays, right? And it will congest the network.
What delays? At the moment when you speak about delays, you speak about restrictions,
sure,
which you have not introduced, which means that transaction of information requires some time, probably.
Yeah, so
also each node has its own, I don't know, processor, its own memory, its own, it has its own frequency of working processor. I don't know. It's something which I have never thought about. But there should be some restriction which doesn't allow to simply make a total flow of information, and then everyone knows what happens
Sure.
with everyone. Everyone knows all coordinates, internal state of every node in the net, and there are no problems, more or
Sure. I
less.
mean, yeah. So this is modeled in continuous time, of course, but at the end you will implement this in discrete time. And motivated by the problems that you have in discrete time, you constrain this to have one hop communication. You communicate only with your neighbors, and you do not try to send information in a multi-hop fashion, right? I want to send something to a node that
Why
is very
not
far
to
away.
try? Why not to try?
To try not to
That's
congest
what I
the network.
ask. Why not to consider some trivial way? I see that it
Yes,
is forbidden. I see that these are the rules of the game. But I just want to understand. I would like to understand why these are the rules of the game.
yes,
For
because
today, all agents are. It seems to me that each agent will have artificial intelligence by itself. Maybe will be cleverer than me. I don't know.
yeah. So
So
it
what
is
constricts
essentially
them?
it is essentially what the people in this area have learned, and is that you have these two solutions: flooding, which is what you're describing, and
Yeah.
this one hop communication, right? So if you compare the two in practice, right? So one congests the network and the other doesn't, right? So the question is, if I can do it without congesting the network, well, I will prefer doing it without congesting the network. Okay. So one hop communication is preferred.
It all
It is
depends.
not that.
Yeah, it all
Yes.
depends on the abilities of the network.
Yes. I mean, there will be cases in which it may be, let's say, an overkill to do this, right? So you may try to, if it's a network of three agents, well, maybe it's more useful to just share among all of them. But if you have
Yeah.
a very big
If
network,
each agent sees 5 agents and there are 100 agents, so then there is a solution when each one sent to each one, and it takes time. Or
yes,
or each one uses only information from its neighbors, but to get the information also takes time. I
yes,
mean that some kind of delay in discretization is not my field, but I feel that at that moment, Emilia, if she's here, should
He is not.
it's
react.
not. Yeah,
It's
yeah,
delay appears naturally here.
yes. So one thing is that we are not modeling delays, but
Yeah,
we
yeah, I
know
see.
that, but we know that one hop communication will help with delays. Why? Because if you have delays and you want to communicate across the network, well, that will take time, right? So if by construction your solution is one hop, by construction you will in practice when you introduce delays will help with that, right? So that's the
But
intuition.
you
Of
still
course,
want to have the outputs.
yes,
And when
yes,
you
of
have
course,
the outputs, you still get information from all the nodes. There is something you see. I just think that the model, in fact, should be much more complicated, maybe.
yeah,
But
I agree.
it isn't done. I understand. It will be quite different theory, much more complicated.
Yeah,
Uh, but I just thinking aloud.
no, for sure. I totally agree with you. And I mean, we have some extensions on the review for the case with delays, which is a more realistic environment. And I mean, of course, with delays, you won't have exact convergence, right? As you mentioned, information needs to
Surely.
propagate across the network, right? So, but you can extend this to delays for sure. I mean, there are. I haven't talked this in order not to, let's say, distract a lot from too many variations, but of course, there is some theory to study delays in this case, and we have done it, but it's not published yet, of course.
For example, if the time uh, of information transaction from one node to another is 1 millionth of the second, and there are, I don't know, 100 nodes, you probably in 1,000th of the second, you will have often all information on the nodes. And then with such sampling period, you may get very high accuracy, especially with high order sliding modes. It's everything is, it depends.
Yeah,
And
sure.
and another question which I have not understood. So you measure SI is the same signal but with different noise. That's what I
Uh,
understand.
that's one possible, let's say, configuration, but then the most general, let's say,
They are
the most,
just different signals. Yes.
there are different signals, yes.
Yeah. Okay. And in the differentiator, which I have looked at exactly at the slide at the moment when I started asking, I just haven't understood.
Let me go there.
At the end, I suppose it was at the very end, something like this.
Yeah, let me, I think it was like this
Uh,
equation, this one,
yeah,
maybe.
maybe here. Yes, yes. I don't. I look. I see that it is something which I should recognize, and I don't recognize it fully, for I don't see where SI enters.
Yeah, so SI enters here. So this is what you implement. This is like the equivalent version to the differentiator. So here, xi0, I mean, if you look at this equation, so xi0 will be
That's
Si.
what it is. It's a definition.
Yes, it is a definition of.
It's not the state of the node.
Yes, so x is the state of the node, right? But we define it in terms of this auxiliary variable, let's say. So if you expand this, let's say,
Okay.
so
Okay,
we
you
have here,
want xi0 to go to si,
yes,
but
exactly.
at the very, but it means that in the mm, it, you need uh it. I would say that you need si measured, which means with noise, minus xj in the brackets. Otherwise, I
Yes,
don't see how SI enters the system at all. I
yes.
see
So
only the last derivative, which one doesn't know. It's a result of calculations already.
for sure. So in this system, I mean, if you expand this particular term, you find this, right? So instead of thinking about x, if you think about
It's
eta,
at the I don't, that I don't understand at all. Yes, sorry. Okay, it's auxiliary variable. Yes.
yes, the
Yes.
auxiliary variable, yes.
So
So one
okay,
possible,
it's not simple for me. I have to reread it, yeah, in order to understand.
yeah, one intuition for this is that these auxiliary variables actually are computing whatever you need to, let's say, subtract to the local signals in order to reach the average, right? So these auxiliary variables are differentiating in some sense, or are computing, uh, let's say, the remainder of the average. Okay.
Okay, okay,
So
okay,
in some
okay.
sense, this is a differentiator. If you look it from the point of view of data, a differentiation from whatever you want to you need to subtract in order to obtain the average. Okay. So in some sense, you can see this a connection to a differentiator, right? But of course, the
Oh,
connection is not entirely direct or trivial. I mean,
I
I
start.
tried.
Okay, I start to understand. You
Yeah.
in the brackets you have the zero order row of differentiation for each node, and you get
Yes.
difference of them. Okay,
Yes. Exactly.
okay,
Yes. Exactly.
okay. So there is inside. Yes, yes. You have written it's above. Okay, inside we get Si and Sj. Okay, okay. Now I understand.
Okay. Thank
Thank you.
you.
Thank you very
Thank you,
much.
Professor Levant.
Okay. So maybe Professor Pajmovic can tell something if you want. Hi, everyone.
Hello. Thank you, Rodrigo. Very interesting talk.
Thank you.
I was wondering if you have some intuition on how one could design the Lyapunov function for proving convergence here.
Yeah. So the only thing we have come up at the moment, so is knowing that there is this connection, right? So for three graphs, there is hidden in the structure of this thing, there is a differentiator hidden, or a set of differentiators, right? So it is rather complicated, but from here you can construct a Lyapunov function, right, for the three graphs, okay? And we have tried to use that same Lyapunov function for arbitrary graphs, and it doesn't work for some reason. And that's the current state of the of what we have, right? So the intuition is this, right? That due to the structure, there is somewhere a differentiator in recursive form. So from there you can come up with a Lyapunov function. But this is just for a particular class of graphs, okay?
So what is the property of the tree graph that allows that Lyapunov function to work, but not if the graph is different?
Yeah, essentially that when you, let's say, write this in recursive form, and recursive form I mean when you inject, let's say, the derivative of one state in the dynamics of the second one, right? So when you do the algebra for this, right, since this matrix is essentially invertible, okay, when you do the algebra, these matrices disappear, okay, inside the next states, okay. I guess the let's say the reason is not very evident, okay, but in three graphs we can make this, let's say, solving for a state in terms of the order and substituting, okay.
So
that's
how
what
about
you can do.
I don't know, this may be very silly, but decomposing an arbitrary graph as a tree graph plus some loops, and using some sort of small gain argument for the loops and the main Lyapunov function for the tree graph.
Yeah, that's the actual proof for the arbitrary graphs. But the problem is that maybe you can do it, but I couldn't find. Let's say I can show that there exists a parameter, right, that makes this work, but I couldn't find the exact bound for that parameter, right? So essentially, at the end, the result still was sufficiently high gains. Okay, so that's essentially proof. I didn't do it with a Lyapunov function, but that might be a good idea. But the original argument, which is something as you described.
Great, thank you very much, Rodrigo. Very interesting talk. I didn't know that topic almost at all, so very interesting. Thank you.
Thank you. And I mean, at least I hope that there is some interest, because I believe there are some, let's say, interesting places to contribute here.
Thank you. Maybe Richard will also add something. Hi, Richard.
Hello.
Hi, Richard.
Yeah, hi. I don't think I have a question at the moment. I have to think about it a bit more, I think.
Okay. Professor Moreno, maybe.
Thank you, Rodrigo, for the nice presentation. What is the dynamic? Which is the dynamics of each of the agents? It is first order dynamics, isn't it?
What do you mean? I mean, the agents does not represent, let's say, a physical system.
Yes, but
what we are modeling here,
they do have some dynamics.
Yeah, so
no?
the dynamics are. Yeah.
Or,
So what you do is this, right? For example, for the superbriefing. So this is something that you implement. Okay. So this is an algorithm, let's say, right? This does not represent, let's say, dynamics of an agent. Okay. this represents an algorithm that you execute at each agent to compute something.
So in fact, my question is, I mean, as far as I understand, the algorithm from George and Freeman, I think, this is just a sign function. They do not introduce any further state.
Yes, exactly.
If you use the super twisting, then you introduce an extra state. This which is not in the original dynamics, and in your case, you introduce a number of extra states in order to describe,
Yes.
isn't it? Mm-hmm.
Yes, yes.
Okay, so I mean, you do that because you want to estimate not only the signal, but also all derivatives up to some point. Mm-hmm.
Yes.
Okay. Well, and why do you say that the Lyapunov function do not work? I
mean, first, you try to show that the Lyapunov argument works, and it gets very complicated. And also, you simulate it, and I mean, the Lyapunov function does not decrease at all times, right? So, one might argue that it's an artifact of the simulation, but at this point, I'm not very convinced that is the case. I mean, maybe the Lyapunov function is something similar to that, right? But maybe I haven't spent that much time trying to come up with a clever, let's say, Lyapunov function. Yes, so if the question was if the Lyapunov function constructed from the Lyapunov function for differentiators, let's say, that particular case doesn't seem to work, right?
Even
So
for
this
the
is not-
super twisting, you mean?
Yeah, even in this case, I mean, if you have a network of two nodes, just two nodes, it works. The same Lyapunov function.
Okay.
Right? But in any other case, not, because you have, I mean, you have many terms here. I mean, what you have to study is actually this system, right? In vector form. And you have these matrices, these incidence matrices, which are bothering you in some sense, preventing this to actually be a proper differentiator, right? In the usual structure.
Where do these D matrices come from? I mean,
this is the incidence matrix. So these differences can be, let's say,
okay.
written in compact form using this.
Depending on where they act on. Okay.
Yes.
Okay. Mm-hmm. Okay, and it is not usual that the agents themselves have some dynamics, or because in this case they do not really have a dynamics, or
yeah. So usually you pose it as a separate problem, right? So you may have a leader following problem, for example, and you want to estimate, let's say, some signal and then track it, right? Mm-hmm. So maybe you can estimate the signal that you want to track using this kind of algorithms, and afterwards you design a controller for that signal, right? So this is like the composition of the problem, right? But let's say we are not thinking at this point on that the agents have some dynamics, and we want to, let's say, design a controller to reach consensus directly. I mean, end to end. This is just like a previous block that is just computation. I don't know if that answers your question.
Yes, I guess this is a much more complicated problem, basically, because the dynamics of the agents, they will make problems in the differentiation.
Yes, yes, exactly. So in this case, we're thinking of the dynamics as something that we can just come up freely, okay? We're not constrained by some dynamics. So we are trying to come up with some dynamics that help us compute something, right? Rather than trying to control or let's say synchronize some systems.
So this means that, does it mean that for you an agent is just something which produces a signal?
Yes. It measures this signal in some sense, or it's it has it, and it can compute and communicate. That's all that it can do, or at least all that what we need it to do, right?
And
It means
how
that
you are
it's a net
using
of
it?
computers. Yes.
Yes, exactly.
Okay.
Yeah.
How you are using, how you are using, how you are choosing the M parameter.
Yeah. So, for example, in some particular problems, I mean, previously we talked about distributed state estimation.
Mhm.
So perhaps each of these signals is just a common signal plus some noise, right? And this signal might have some dynamics, right? So according to those dynamics, you may choose M, right? So in that particular case, that can give you the intuition of how to choose M, right? In the general case, well, it depends, right? Just as before.
So it is part of the parameters you should know, is a set of parameters you should know beforehand.
Yes. Yes, that's one important thing, right? So all agents agree on the order of the differentiator, right? So that's important.
But should be it the same for all of the agents, or each could be individual?
No, it needs to be the same for all agents.
Mhm. So, but okay, thank you. So, but can you, for example, make generalization of this problem, giving the different M parameters individually, and then maybe for the proof to use a Lyapunov function with the same homogeneity Y? Because for each differentiator, you can grow the degree of the function according to homogeneity, white and you're willing, and then you make them similar for all the agents, and then try to prove other or something.
Yeah, perhaps I haven't thought about that, but it sounds reasonable, I guess.
David, are you also working with similar problem or not?
Yeah, we are also exploring working with the predefined time and also applying this for synchronization of agents.
So, and that's the reason I was asking, I was waiting for your question, or you are working together with Rodrigo for a long time, so you have plenty of ways to discuss the story.
Yes.
Yeah, so thank you very much, Rodrigo. Very nice presentation, a very nice exposition. I do have a few questions. Can you comment also about the robustness if an algorithm, if one of the nodes is not following the behavior of the differentiator?
Yes. So if you have, let's say, or what do you mean the behavior of the differentiator?
Yeah,
I mean, if you have
one of them is not differentiating and just sending repeating the signal, right? It's not computing the algorithm.
Yeah, yeah, that is a very interesting question. I haven't thought about that particularly, but I guess I mean these terms, let's say, so you will have some extra terms given the nodes that that do not follow, let's say, the dynamics. So this will make disturbances, and interestingly, yeah, they will be like additive disturbances. So maybe you can bound convergence in some sense, right? But I'm not sure at the moment.
Will they bias the derivative or it will be like rejected? I mean, suppose you have 100 nodes and one is misbehaving, right?
Yeah. So for this particular algorithm, I think it will ruin everything. But there are some extensions. Let me see. I have some. So there is an extension of this algorithm in which you introduce these damping terms, which allow you to have some form of robustness against these kind of things. So maybe this will help. The only problem with these damping terms is that they destroy homogeneity, so you may lose another thing. So it's a trade-off. Up to this point, I think it is a more difficult problem what you're describing.
Okay, okay. And also, can you put the drawing of the graph? So
Sure.
in the linear case, you will have a small error between each agent, right?
Yes.
And that will accumulate among the network, and you will have the error between the smallest value and the higher value will be large, right? So this is also
Yes.
a motivation to be more precise between agents, and also to try to apply finite time algorithms, right? Because
Sure.
of the exactness of the at least in the continuous time, right? But also in the discrete time, you may have better precision, right? Among the
Yes.
network.
Yes, I mean, in general, I mean, this is very hard to show in general, but from, let's say, practice and simulations, you can actually see that as you increase the network, these type of algorithms are more precise than linear and even standard sliding modes, right? So yes, it seems that the accuracy improves, of course, with the higher order sliding modes, even with delays, but showing that formally is still very hard.
Yes, challenge. Okay. Okay, I think I don't have any more questions. Thank you very much. Very good presentation.
Thank you.
Thank you for this. Thank you, Rodrigo. So, other questions, please. Okay.
Well, actually, I remember another one. So you mentioned that by doing distributed sensing, you can reduce noise, right? Can you have also reduced chattering because of, or what happens with chattering?
Yeah. So
I mean,
one way in which you
numerical
can, let's
chattering
say,
here, right?
yes, one way in which you can, let's say, quantify chattering is this, let's say, very standard argument. Let me just go for it. So essentially you know that, let's say, the accuracy when you have discrete updates in these terms in the communication, you can show that it is of this form, right? So for the mute state, right? So the error increases with this delta, which is let's say the delay, up to some power, okay? And of course, as you increase m, this gets smaller, but for only for smaller for small values of the sampling step. Right? So using let's say comparison between different powers, you can show that chattering gets better, or you can reduce chattering, let's say for small sampling steps, using a higher order.
No,
Algorithm.
but I mean, if you have a centralized differentiator, you will get some numerical chattering with some discretization and sampling rate.
Yes.
And if you differentiate that signal distributedly with this algorithm, the chattering level is improved or is worse?
I think it will be worse.
Okay.
And it's related to what Professor Levant said earlier. I mean, this depends on essentially on the maximum delay that you can have. And if you have a delay between two nodes, the maximum delay, it depends on the longest, let's say, path that you have, right? So it increases with the network.
Okay.
I mean, of course, of course, if a signal is varying a lot, right, and it's very far from you, right, so you won't be able to catch those variations. So that will make it worse in some sense. I don't know if that answers your question, David.
Yeah, very interesting work.
Thank you.
Thank you. So, thank you for all for, if there is no more questions, thank you to all for participation. I hope that we will continue working, and you will continue coming. Next Wednesday we will have a seminar by Gustavo Rueda Escabeta, and he will present his own topic. I don't know if Gustavo is here. Gustavo, are you here?
I haven't
So-
seen him. I don't think he's here.
I also haven't seen him. So anyway, I will send an announcement with the abstract of the talk and topic of the talk. And so see you next Wednesday. Thank you already once more for presentations. Thank you to all for coming. Thank you.
Thank you so much, everyone.